Good afternoon. I'm Paolo, and today's talk is about preserving confidentiality when hunting with friends. That's the agenda for this talk. We're going to talk about a real example, which is the Trigona campaign. Hopefully, some of you have heard of that. The way that security operations would have worked in this specific case. The incident response frameworks and standards that you could have used to share this specific information, and an example of cooperative threat hunting. So this is the traditional part. Then we start to introduce this new concept of pets, which are not your cats and dogs, but it's privacy-enhancing technology frameworks, and three main approaches to this technology. We then explain why we chose MPC and DP. These are all acronyms that you are going to learn, so don't worry too much. And finally, we're going to share a real deployment of this combination of technologies that is being used in the Netherlands. And then we basically leave to a session of Q&As. OK, so I'm Paolo. They call me the Doc. I can't remember who found this nickname. I currently work for a startup called Priam Cyber AI, based in the UK. What we do is security operations empowered with AI, ML, but specifically focusing on differential privacy and cognitive neuroscience. Prior to that, you might remember me for working at Fortinet as a senior data scientist, and before that, I worked in Microsoft in a variety of roles. I also contribute to some of these projects you might have maybe listened to and one of these workshops. So I work for I do some stuff for the OASIS, specifically the STIX 2.1 format, and the EPSS, which there were so many sessions. And I also work for the MITRE Engenuity project. So enough about me. I'm going to give the ball to Mr. Gabriel.
Hi, so I'm Gabriel. What we have in common is that we are both former lead data scientists, you for Fortinet, me for the DBIR. What we have not in common is that while you have an amazing PhD, I do not. I can only aspire to such things. I'm currently at Liberty Mutual, which, plug for the insurance industry, it's actually a really interesting place to be in cybersecurity. But other than that, I've done a couple things you can see up here, and that's not the fun part of the presentation. So I hand it over to Hugo, who's also got a much more interesting background than mine.
Thanks. So my name is Hugo Ideler. I'm the head of engineering at Roseman Labs, which is a startup that specializes in multi-party computation. I'll talk more about the technology during this talk. I'm also part-time at NCC in the Netherlands, and also there focus on multi-party computation. In the past, I was an IR practitioner myself, so I have a good understanding of the needs of professionals in the field for sharing threat intelligence with each other. Now, maybe let's talk about the Trigona campaign. Gabe, can you tell us more?
Sure. So we want to start this presentation off with kind of an example of a campaign. So there's nothing fancy about this. This is something that comes from kind of a Palo Alto and an Arete reports. And it's a very straightforward campaign. There's no fancy zero day. It's just a known CVE that led to lateral movement, that led to exfiltration, then ransomware. And so the point we want to make about it, though, is that there's a lot of places where you could detect this, right? Your EDR can detect it. Your antivirus could. You can detect it at the network layer. You can detect the PowerShell. There's a lot of visibility into it. But the question is, are you as your own organization going to really get all that visibility? And so what we did is we wanted to make the point, particularly, this is the first of the major points in the presentation, that it takes structured data to be able to utilize what you can collect. And so on the left here, you'll see kind of the fast, the detailed, the tactical data. And this is good, but a lot of times we're collecting in the moment. And so we don't necessarily have the time to tag it to figure out what's shareable and what isn't. a lot of it now may be kind of coming from unstructured data, but if anyone was here at the AI large language model meetup yesterday? Yeah. So we may start being able to use large language models to pull out named entities from that data to help us structure. On the other side, on the right side, we have the higher level, the slower, the more shareable data because it's been reviewed, it's been approved, and there's this connection between these two sets of schemas in that we want to kind of connect them. But what we'd like to be able to do is get that right side, or excuse me, the left side to operate the same way the right side does from a sharing perspective. And so, sticking with our example, we took the Palo Alto STIX package for the threat set, and we simulated and we said, okay, we're going to have 4 companies, all that have different detection capabilities. And we're going to see what they see in common if they were all to see this threat set. And what we found is that there were 30 indicators and 7 patterns that were seen by at least more than one company. But there was also a bunch of stuff that only one company saw. And so ideally, what we want is for all 4 companies to be able to share with each other quickly to establish that context around what was happening. But I don't think that that's what really happens a lot of times in the real world these days. And so let's take an example. Say I'm that first company that's detecting this attack, right? And I've got a little bit of context here. I'm seeing just a little bit of this behavior, but I don't really know whether that behavior is legitimate or whether it's malicious, right? Because I don't have a lot of context. What I really wish is that I knew additional context. Now, by the way, I'll mention this while we're on the slide. So you see like the dots and edges over on the right. This is kind of a take on AttackFlow, which MITRE CTIDs work on. And this is a little bit modified to work well with graphs, particularly knowledge graphs, which is a great way to structure this kind of data because it represents the relationships between it. And so the nice thing about knowledge graphs is there's a lot of existing tools to support it. You don't have to go out and build from scratch. You don't have to start from nowhere. There's an entire ecosystem around it. It's a great way to store this kind of data because you can get that really rich context and relationships. You can get the causal paths, right, the links between things, and you can represent the complexity. And so that's an aside. Getting back, we've got a little bit of context, but we really want to be able to get context from someone else. And this is company 2. In company 2, they saw the same thing I did, but they saw a bunch more. And the problem is this additional stuff, one, they can't share this because they really haven't had the time to go through it and figure out what they can share. And then the bottom side, they really don't want to share because it's a lot of sensitive information. It's information about the inside of their organization, how they're structured, and that's things that are not easily shareable. And so they continue to investigate, and they come up with this huge amount of context around this incident. And it's context that I need as an organization, one, to be able to figure out what's benign and what's malicious for me. But the problem is, even if they can get to where they can share that top bit, the TTPs and such, they're probably never going to get to where they can share that bottom bit, that TLP red information about the inside of their organization. And this is the crux of the matter. We want to be able to share that. We want to be able to share it with time. We want to be able to share that sensitive data securely. And so, Paolo, is there any way we might be able to do that?
Yes, of course there is. Otherwise, we wouldn't be here to present these slides. So the idea is, so assuming you worked out all the basics, so you have your data models, you're using VERIS, AttackFlow, Cacao, et cetera, that you have seen in previous talks. You then have this problem of building this shared knowledge graph, but without the red tape. So, and you have to do this fast enough that you want to beat your adversary because it doesn't always take 4 months for a ransomware campaign to complete. Okay, so we can talk about these paths. What kind of paths we're talking about? So they're being used as a set of techniques or technologies that have been used quite many years ago. They're not specific to cybersecurity, Mostly they come from like the medical field, releasing public health data sets. And some of them are intuitive, so generalization means you summarize a data set, suppression means you remove specific entries, randomization, you shuffle some of the rows in the data set, pseudonymization is, you use aliases, etc. So there's a lot of techniques. But the problem with these techniques is that they don't offer a strong notion of mathematical guarantee for your privacy. So they are not very applicable to cybersecurity. So what you need is, a Sheldon from my favorite show. I don't know if many people know that guy. And the brain of a genius with the operational capability of an A-team to deploy something that you can trust, right, in terms of guarantees. And it is performance enough to work on high volumes of data. So in practice, yes, there are many technologies you could adopt, but there are only 3 of them, which we mentioned in these slides, that are somehow applicable to cybersecurity. So on the left side, there is the picture of a snail. I'm not sure how many people are using FHE. There's no a personal attack on FHE. I believe it's a great technology. But in practice, for high volume of data, there is a high computational cost. Yes, there's a low communication cost, but it just doesn't work on cybersecurity on the amount of data that you can get in our use case. Then we can talk about multi-party computation, MPC, from now on. So it's kind of the opposite. So there's a low computational cost, but there is a high communication cost when you run these protocols. And there is a picture of a beetroot. I don't know if you can recognize that plant. But it was used since 2008 in Denmark for beetroot auctions. Well, it's like people will laugh at Europeans, but it's kind of an important market that has been regulated. And yeah, they basically using MPC to do these kind of auctions to make sure they are fair and people are not tampering and all sorts of problems with the pricing of these very important vegetables. And then for the differential privacy, maybe you have heard of this. Actually, it was discovered by a researcher in Microsoft at the time I was working, so I actually talked to her in person. And they are very fast to compute. They support most queries, but there are some trade-offs. So the trade-off is accuracy versus privacy. And there's a logo of a stethoscope from the medical field because most of these applications were used in health data sets. So if you're from the US, you're probably familiar with the Census database, which is done every 10 years, I believe. Yeah. And some naughty researcher had this idea, hey, I can do a linkage attack to this public release data set from 2010. And he managed to re-identify 50% of the entire US population, right? So it's pretty big. So he was able to find names, addresses of people in the census data set. So US government went crazy. It's like, okay, we have to we can't keep doing this. This is quite dangerous, right? We have to find some ways to protect the future release. So the 2021 is actually protected by differential privacy. So they're using this very technique. So this is kind of one of the biggest examples, but there are so many other ones you can search online. Okay, so I'm going to try to simplify. I'm quite into this topic, so I'm trying to simplify differential privacy with a kind of an example. So let's say you have a team that you want to feed and keep happy, and they like to eat bagels, right? So every day. So you want to make surveys every day from your team about how many bagels they're consuming, because maybe you need budget for next quarter to have enough bagels. But of course, this can be a sensitive topic. If you're on a low-carb diet, you don't want to say, well, I shouldn't be eating bagels by 800 a day. So, I don't really want. I'm not very comfortable to do this survey. I mean, this is kind of a silly example, but they've been using this in serious surveys, like drug addiction. Have been using particular type of drugs or there's like lots of serious examples that you can also think in cybersecurity. So the idea is like, what if I give you some guarantee that if you join this survey or if you don't join this survey, the statistical output of that will be identical. So there is no mathematical, there's a certain level of probability that will guarantee that nobody will be able to re-identify you in that data set. So it's probabilistic, it's not 100%. It can be 100%, but if you say, well, I want to have a 100% guarantee that I'm not going to be, nobody is able to re-identify me, it becomes impractical because the entire database is useless, right? There is no more correct information, like it's mostly random. So the way they solve this problem is quite simple, like it's add random noise. So let's say you have, we have like 100 team members or like 50 team members. So we teach them a protocol and say, okay, so Paolo, you go first. You don't have to tell me anything, but I'm going to tell you this. So you take a coin, like head or tail, and you flip it. Okay, it's a fair coin, right? You can test it, like I'm not cheating you. So if he's head, you're going to respond me with the truth, right? So like if I eat 2 a day, I will just say 2. But if you get tail, you can provide a random response. So you don't have to tell me the truth. So Gabe, maybe it's 3 bagels a day. He's bigger than me. And oops, tail. So I'm going to say 4, right? There is of course a range of values that you have to provide. You can just say 100,000. There is some. I mean, I'm trying to simplify that. You can add, let's say, +1 or -1, right? There's intervals you have to follow. Okay, Hugo, like let's say is 5, and okay, gets a tail and says yes, says 3. So at the end of the day, the true daily consumption of bagel, let's say, is 100. Like, okay. Now, at some point, your HR team wants to do like some statistical analysis and say, well, I want to see like a daily how much bagels my team is eating, and like okay, all these IDs are anonymized, of course, like so they won't see Paolo, Gabe, and Hugo, but they will see all these counts. So every time you do a query into this database, which is a special database, you will get different responses. So which is kind of weird, right? So like John from HR will do a query like on the same day, and the response will be 120, right? It's not 100, right? Like team will get 90, Ryu will get 150, okay? And this database is designed in a way that if you perform enough amount of queries, the average of those responses will be exactly 100, okay? So in terms of guarantee, like what shouldn't happen is that you shouldn't give the user of the database enough queries to be able to reconstruct the true value, right? So that's the entire point of differential privacy. So there is a clear trade-off between accuracy and privacy, right? So like the more noise you introduce, the more random, like let's say inaccurate data you will get. On the other side, if you provide the correct answer, it will be easier to identify who was in that data set, okay? So now we go to another example, still with bagels, but with multi-party computation.
Yes, we stay in the concept of Montreal bagels. And here I'm going to show you an example of a multi-party computation protocol. Multi-party computation is a technique for which multiple protocols exist. What I'm showing you here is a very simplified example. In practice, we use different protocols in the real world. However, the concepts are the same. And what I'm going to show you is how you can do addition under multi-party computation. Multiplication is more complicated. I'll not show you that. But the question here is, Gabe and Paolo both have a number of Montreal bagels, and they do not want to disclose their actual possession to each other, but they do want to know how many they have together. How can they do this? Well, you can do this using multi-party computation, and what will happen is Gabe and Paolo will take their stack, and each of them will split their stack into 3 substacks of random values, but those values need to add up to the original secret that Gabe and Paolo have in mind. So far, so good. And say, for example, that I am node 0 in the middle of the page, then I will be receiving the numbers 3 and 2. The next step is that every of these MPC nodes, they add the numbers together that they received. So again, if I am node number 0, then I add the 3 and the 2 and I get a 5. Finally, all the MPC nodes, they add their numbers together. And as you can see, if you add those numbers together, you get 16, which is also the addition of the original secrets from Paolo and Gabe, which is also 16. So using this method, we were able to construct an answer, the addition, without revealing the inputs of the parties. And all the helper nodes, the values that received, they could not reconstruct these values towards the secrets that Paolo and Gabe had. So even if you hack one of these nodes, you would not learn anything about the original secrets. Knowing this technique, let's discuss how we can use this for threat hunting.
Okay, so you're probably familiar with this architecture. So you're using, let's say MISP to consume your threat intelligence. You probably have TLP colors. You have a private MISP and a public MISP, and your analysts do this kind of queries. So the good news is that you don't have to change your modus operandi. So you can basically perform the same queries into this new kind of engine. I've listed some of them, so you can do, give me a list of all malware hashes within this database. What are the TTPs for specific ransomware, et cetera, et cetera. The only difference is that your privacy engine that sits at the center of this multi-party computation will basically decide, based on policies, and we talk about later, what is allowed and what it isn't allowed, and what kind of techniques should be applied. So, for example, very simplified SQL queries, most of you will probably use these in other tools, is, okay, I want to know, for example, how many companies are joining into my trusted group of SOC teams. The engine say, oh, this is green, okay, that's fine. I can tell you that number is 10, right? So this number can be protected by differential privacy, so it might change. If you enable that, it's totally up to you, according to your policy. Now, like maybe you have another analyst, maybe he's a little bit more curious, so say, well, I actually want to know like which companies and their names and locations that are within this group. And we say, well, that's not really something we want to really reveal because I don't want to, reveal the companies within this group. So the engine will say, well, there is actually one, there's 10, there are 10, but I can only give you the name of the company that you already know, so which is yourself, right? So it's just going to give you one. You can do joins or unions. There's a kind of a bit more sophisticated query over there. It doesn't matter to the engine. There will be the same codes and say, well, like in this case, you want to know how many companies were affected by the Trigona campaign. And it's going to tell you, yes, it's 4/10. And everything was basically encrypted, and none of that information was leaked to anybody. Okay. Now, Hugo is going to give a little bit more details of how this thing works.
If you want to use multi-party computation for threat hunting, one of the approaches you can take is how you see it in this diagram. You see it with 3 parties, but you can add it up to as many parties as you want. And each of the parties, they use the same splitting concept that I showed with the bagels. So instead of splitting a pile of bagels, you could also say you take, in the case of compromise, and you split those into a number of parts. Those parts are then submitted to the privacy engine, which are those MPC nodes which run at different organizations. And then on the right, you see the analysis interface. And that is also an important part, is that multi-party computation as a technique by itself has no opinion on what computations that you will be performing. Therefore, as the parties taking part in this cooperation, you need to agree on what is an allowed analysis. So for example, yes, you're happy to share IOCs, but you don't want to reveal who has supplied this IOC, as an example. So therefore, you need to have a governance structure around which queries are allowed. But this can be expanded up to as many parties as you want. How can we build such a tool?
I'm going to go over this a little bit quicker, so a little bit late. There are a lot of tools that you can use from the open source community, so I've listed some of the most popular ones. But the idea is that, yes, you can do all of this. It's hard work. I'm not going to lie to you. You have to combine multiple technologies, but you can actually build this on your own if you have the willing to do so. So yeah, there's a list of tools that you can use to do that. Okay, so let's go to a more interesting example where we actually deploy this in a real setup.
Yeah, so the National Cybersecurity Center of the Netherlands, they are using multi-party computation as part of one of their products. SecureNet is a product from the Dutch Cybersecurity Center. It's called SecureNet, and it's also already in production. It is being used by organizations. And as you can see, there's a public web page. You also see a screenshot of the interface. And how are they using it? In the early example, we had bagels, then we had indicators of compromise. In this example, we have surveys. NCC is using this tool for organizations to share information that they are not legally required to share, but they are asking these organizations to share them in order to help each other. But as you can imagine, there are also companies in reality that are not too keen on sharing very sensitive information, for example, because the CEO is scared that the information might be leaked and the stock exchange might crash for them. So therefore, NCC thought, let's use multi-party computation and use it in such a way that you can guarantee to the organizations that their information will be anonymous, which may lead to a higher willingness to share information. So these organizations, they fill in the surveys in step 1. The results of the surveys that they supplied are also secret shared on the client side. These are then sent to NCC, and they do analysis on this data. And again, the analysis that they need to do on this data must be something that is in alignment with what the participants agree with. So if, for example, you ask for a number, you could say, we take the mean and the standard deviation. NCC processes these results, they create a report, and this report is shared back with the participants. So you have a feedback loop that leads to higher cooperation between the government and the NCC with the organizations from the private sector. Having heard all these potential solutions, maybe it's time to wrap it up in a summary. Gabe, can you help us?
About that time. And so, hopefully, what you've taken away is that, one, we really have this need to be able to share data and share sensitive data quickly and securely. And we really believe there's these two things that do that. There's having strong data models, and we're lucky enough in this industry to have some good structures around our data. And then there's having the strong algorithmic capability. And that's where the differential privacy, the multi-party computation come together. And really with those two things, we can actually start to share sensitive data securely. And so with that, if you want to get a hold of us, if you want to learn more, join the Slack, the bit.ly or the QR code. Please email any of us if you come up with stuff after the fact. And with that, I think we have time for maybe one question. Maybe. Yes, we can clap. Okay. Yeah. They can't hear your mic.
I was commenting that I had a project ages ago where I was trying to study password selection, and the idea was that I needed to know that people were using the same or similar passwords without knowing what the password was. So of course it involved a hash and extra layers of computation to conceal it, and a lot of people don't realize how useful that can be. And obviously, you're demonstrating the value in being able to share that stuff, but still protect it at the same time. Other questions?
Oh, they're going to let us off easy. Yeah.
Oh, here we go.
Okay. Cryptologists, you're in trouble.
Hi, great talk and great work you did. I was wondering if you are planning to open source anything, make it easier, because you had like a large set of tools that need to be set up to actually make it work. Are you planning to do anything?
And so we're at the stage where we're figuring out how it all works together. Maybe we'll be able to come back next year and be able to make something, have something put together, because I know this is something that's beneficial to the community, that'd be really helpful, and we don't have it now, but hopefully maybe next year we'll come back with a cool tool and we'll just sit down and be like clicking through our UI and showing you all the cool things you can do. So not yet, but hopefully in the future.
Great, thanks.
Thank you for that. Anyone else? Just a reminder, please do fill out the survey forms. You can fill it out now if you were waiting for me to tell you. Yes, thank you again, gentlemen. Appreciate it.